Yes, right. Start doing question number 10, 11, question number 10, 11, 12, 13. So I also start doing, I won't waste the time today. Yesterday, I tried to connect sort out the issue, but could not sort out because there was an issue with the Wi-Fi, fiber connection. So then 10, 9:45 only it started and we come to the class. It's okay, something we plan to do, something we plan something, sometimes all our plans won't happen in the right way. That's a problem with there, but it's okay. My now plan is today class effectively completing. That's my target. That's my target. Mm. First of all, we'll do some questions, and now today plan is to now. I think last day we discussed in rotational motion, angular motion equations. If not rotational motion equations, we learned last day. Today our plan is to discuss. Uh, Now in linear motions, we learned about motion graphs. We don't take that much of time when it comes to rotational motion. We will learn rotational motion graphs as well. And you can remember in linear motion, we learned displacement time graph, velocity time graph, and acceleration time graph. In rotational motion also, we will learn angular displacement time graph, angular velocity time graph, angular acceleration time graph. But we don't take that much of time like in linear motion. I think the overall understanding you have regarding motion graphs. So because we took a long time and I explained how to think logically, and how to plot the graph. I think in motion graph section I taught you. So therefore, in rotational motion, we are not taking that much of time as soon as we are completing. Right? That's the way. Not only me, any teacher who does this lesson, this is how they do. This is the way that we are doing. We don't take a long time like any motion because we are assuming students are now what experienced the logics. So therefore, rotational motion for the last period of 8 9 months. Therefore, we are assuming rotational motion students will be able to understand. Based on that only, we are doing everything. Okay, story done. We are talking about question number. We'll do 2 3 questions and we'll go to the today's part. Then 10 wheel of diameter 10 centimeter rotates in a horizontal plate with a uniform angular acceleration 2 rad per square second. Capital A is a particle positioned at the edge of disk. After 1 over root 2 seconds, find the angular velocity simply. So they have given the 3D view, but I draw only a 2D view. Question number 10. Question number 10. There's a particle in the perimeter of the circle, I think. In the perimeter of the circle, I think. This particle is particle capital E. It's a particle capital E. So diameter 10 centimeter, but in the image it is given as radius 10 centimeter. So we'll consider now in the question diameter 10 centimeter, but in the diagram radius 10 centimeter. We'll take radius as 10 centimeter. R is 10 centimeter. Okay. Angular acceleration 2 rad per square second. Right. Angular acceleration alpha we know. R we know 10 centimeters. So this disk is rotating in clockwise direction. So we'll think in that way. Fine. First, we should find angular velocity of the particle, right? After 1 over root 2. I think initially disk is at rest. Initially disk is at rest. After 1 over root 2 time later, find the angular velocity because the disk is under angular acceleration. Initially it is at rest. Little by little its rotational speed is increasing. After 1 over root 2 seconds later, what will be the angular velocity? So omega naught initial angular velocity is 0. Alpha angular acceleration is 2. I want to find omega no time. Omega equals omega naught plus alpha t. Simple A, the equation is in the clockwise direction. I'll apply omega equals omega naught plus alpha simple t. Then I want to find omega. Omega naught is 0 plus angular acceleration is 2. Time taken is 1 over root 2. So the final answer will be omega is root 2 rad per seconds. Rad per seconds. Not difficult. Can understand. Simple B. Centripetal acceleration of the particle. Last day we learned what is centripetal acceleration, and we learned two equations for centripetal acceleration. One is v squared over r. Centripetal acceleration AC means v squared over r. From that equation we derived another equation for centripetal acceleration, r omega squared. So now since I know omega, since I know the r, better to use centripetal acceleration equals r omega squared. Simple B, centripetal acceleration equals r omega squared. R omega squared. We derived this equation last Sunday. Then R is how much? 10 centimeters. How do you convert centimeters to meters? Multiply by 10 to the power minus 2. Angular velocity omega is root 2 squared. Then root 2 square means 2. 2 means 0.2 ms minus 2. 0.2 ms minus 2. If I ask you what is the direction of centripetal acceleration, keep in your mind, direction of centripetal acceleration will be always toward the center. That part you should have an idea. This story is okay. Am I correct? Then simple C, they're asking tangential acceleration of the particle. You can remember last day I derived the relationship between tangential acceleration and angular acceleration. A equals R alpha. A equals R alpha. So you know angular acceleration alpha is given in the data. Alpha is 2 rad per square second. If you want to find the tangential acceleration, you know that A equals R alpha equation. Not difficult. C A equals R alpha equation. So likewise, like V equals R omega equation, A equals R alpha equation. We derived this equation last day. Then you know A equals, if not you can put AT, tangential acceleration equals radius 10 centimeter convert to meters multiply by minus 2 into angular acceleration is 2. Angular acceleration is 2. So therefore we are getting here 10 to the power minus 1. This is also 0.2 ms minus 2. 0.2 ms minus 2. The last one they're asking angle between the resultant acceleration and the tangential acceleration. Now this part I didn't teach you. You can remember last day I explained what is tangential acceleration. Then last day I talked about what is angular acceleration. But you can remember I told you that I have to teach you one part, but I don't do that part. I will enter to angular motion equations. You can remember, right? That is the resultant acceleration of particle on a rotating object. If when an object rotates at a point on the rotating object, what would be the resultant acceleration? I want to teach that part. But because last week I was explaining some complex ideas, I thought if I teach that point also, I don't know most of you will understand. I didn't do that part. So I will teach you that part after discussing angular motion equations. But temporarily understand, now you know what is tangential acceleration AT. You know what is centripetal acceleration AC. The accelerations are vectors, right? So I told you always, if I draw a circle, if I draw a circle, you all know that. Roughly, I will tell you. As a theory, I will teach you. Don't worry. Circle. Just now I told you centripetal acceleration always acting to the center. This is your center. I taught you centripetal acceleration. When that particle is somewhere here, right? When the particle is somewhere here, it's marked somewhere here. Then at this instant, now this is continuously rotating. Imagine what's really happening. You want to imagine. It's continuously rotating. When you freeze a certain instant, if you can freeze the time, a certain instant, this is the location of the particle, direction of centripetal acceleration, always to the center. This is AC. And tangential acceleration direction, always tangent to that particular point. If it is rotating in clockwise, this is the direction of tangential acceleration. So, what is the conclusion? I will teach the story as a theory, don't worry. The conclusion is we know always centripetal acceleration and tangential acceleration, they are perpendicular. They are perpendicular. So, if you want to find the resultant acceleration of AC and AT, if you want to find the resultant acceleration of AC and AT, you know how to find the resultant. You know how to find the resultant, you know that story. That story we learned. It's vector story. So last part, simple D. Okay. Simple D. There are two accelerations. So you also keep on doing. So then we know. I say the centipede. For an example, your tangential acceleration is this direction. AC, according to this question, AC is 0.2. Then, okay, this is tangential acceleration. Centripetal acceleration is in this direction. Always they are perpendicularly. They are perpendicular. Then the resultant will be. The resultant will be in this direction. The resultant direction will be. Resultant acceleration will be, let's say, capital R. So they are asking angle between the resultant acceleration and the tangential acceleration. Angle between the resultant acceleration and the tangential acceleration. That means I want to find this angle. I want to find this angle, but here you don't want to find the angle. Automatically, you know why. Because centripetal acceleration also 0.2, tangential acceleration also 0.2. Your AC also 0.2, AT also 0.2. Then reply everyone in the chat box. Reply everyone in the chat box. What should be the uh, angle T alpha? Now, don't you think alpha is angular acceleration? This alpha means here I mean the angle, okay? Then what should be the alpha value? What should be the alpha value then? Reply everyone. Reply everyone. In the chat box, put a reply quickly. What should be the alpha value? What should be the alpha value? Anyone? No replies. What is the alpha value? Vibashi and Namaya, can you tell me the alpha value? 45 degrees. Because we know in vectors we learned when two vectors with equal magnitude, the resultant will be the angle bisector. Angle between these two vectors 90. If magnitudes of these two vectors are same, the resultant will be the angle bisector. Then this angle must be 45 degrees. Angle must be 45 degrees. Angle must be 45 degrees. That story is done. So alpha is 45 degrees. If not, you can use vector equations and you can find the answer also. So 10 is done. 10 is done. Okay, right. So now likewise we can do questions. Likewise we can do questions. Just keep on doing question number 12. Just keep on doing question number 12. Keep on doing question number 12 quickly. Keep on trying. Question number 12. Hands up whether everything I explained you can understand, right? Hands up. Can you hear what I'm speaking? No issues, right? Okay. Right. Because now we have to do some additional classes, right? Can it's not compulsory, but by thinking about your side only, I thought of do some extra classes. If not in weekend, we for holidays, we don't need to put classes, right? Think about my side. I should not put classes on poetry. But why I am doing an extra class on poetry by thinking about you, because I don't get any extra money from you, right? Even I do a huge number of classes, I won't get any money from you, right? The money is always fixed. But doing theories as much as possible and covering earlier is in my side. If I'm money minded, that it's very what for my side it's gives disadvantages, but I don't think that, because I'm genuinely working with you all. I want to do the things quickly without harming the quality. I want to do the things quickly only, but I don't know, the participation might be not that much. That's okay. uh, because we can't bring all of them to a journey, because I don't know, maybe they might have another other classes, so I don't know, they haven't informed me prior to this also. So I even it's okay, even the participation is very low also very fine, but I have to do it because I want to do my part properly. Yesterday also I could not do the class due to the issues. I started at exactly the right time but could not do what to do, because these connection issues happens sometimes, right? I tried to start at 9 o'clock also, we could not start because cannot do because of the connection. I can't do the class now. Class is okay, right? See, so therefore then it's okay. I want to do this class effectively. Time is 2:55 until 6:65. I will do it. Okay, it's okay. Right. Sometimes there's a small problem. Sometimes the physical class students get a kind of disadvantage because doing extra classes through online. There's a problem in there. Other than that, but if they join, they can cover it. We are not doing theory classes every day online, right? Mostly, I do hybrid classes. Physical, the class where I do physically, I stream online. So but students also want to understand about all the facts, because all the idea is pure, right? Idea is genuine. My idea is to cover this soon as possible, right? Okay, so put your main topic. We'll do the questions, but we'll call theory also. Put your main topic, angular motion equations. Now you understood what is angular displacement, angular velocity, angular acceleration, and now we talked about angular motion equations. Now the next scenario is, after we learned linear motion equations, we talked about motion graphs. Likewise, we are talking here about angular motion graphs. If not rotational motion graphs, write down your main topic. Angular main topic, write down main topic. Angular motion graphs. Angular motion graphs. Number one, write down number one. Angular displacement time graph. Number one, angular displacement time graph. Now I don't go so deeper. Can't teach in that way also. Number one, angular displacement time graph. Angular displacement time graph. If not theoretic graphs, okay, you write on angular displacement hyphen time graph. Inside the bracket, put theta t graphs. Right? Okay. So, if you know what is displacement time graph, the variation of displacement relative to the time we plot in displacement time graph. Very similar thing is there. So, if you can mark the angle, if you can measure the angle rotated by an object in every second, and if you can mark that angle rotated by the object relative to every time, that gives theta to t graph. So, your y axis must be angular displacement, your y-axis must be angular displacement. Angular displacement we know measured in radians. Rad, your x-axis must be the time. X-axis must be the time. Time measured in seconds. Okay. So now, what shall we do now? Then, if I ask you, in displacement time graph, gradient represented velocity. Likewise, what is the gradient in angular displacement time graph? The gradient is angular velocity. Very same story. Only the variable different. Other than that, every story is same, exactly same. So what you can do if you draw a graph, let's say I draw a graph. Okay, if not, we'll draw a graph like this, a curved graph. If I draw a curved graph, if I take a point, this point, let's say point capital E, point capital E. Now you know how to find the gradient. Gradient means when you draw a tangent at point capital A. If you want to find the gradient at point A, draw a tangent at point A, then draw the positive x-axis. Draw the positive x-axis. Then angle measured from positive x-axis to the tangent line in the anti-clockwise direction. The tan angle is gradient, right? The tan value of the angle is gradient. You learn this story. So you can understand. So gradient of theoretic graph, you will draw the graph, write down with me. Gradient of angular displacement time graph. Gradient of theta t graph equals what? Tan theta. Tan theta means we know. Tan theta means we know. If you know in a right angle triangle, tan theta means we know. A right angle triangle, therefore what I do, I try to draw a right angle triangle here. If I try to draw a right angle triangle here, right? This is positive x-axis. If I draw right angle triangle here, what is this vertical line? Change in angular displacement, right? Because your vertical axis is angular displacement. This is change in theta. That means delta theta. Change in angular displacement. Then what is this? Then this one. This is what? Change in x-axis. That means change in time delta t. Delta t. Then tan theta means we know that opposite over adjacent, opposite is delta theta, adjacent is delta t. So tan theta means we know delta theta over delta t. This story is important equation. Write on the story. So red color pen, once you finish writing, raise your hands. Now looky, delta theta over delta t means what? Delta theta over delta t means what? That is the angular velocity. Can you remember how we define angular velocity? Angular velocity omega means delta theta over delta t. So this is red color pen, write down equals omega. Equals omega. Omega means you know that angular velocity. Once you finish writing, hands up. Once you finish writing, hands up. Once you finish writing, hands up. Done. Raise your hands if you finish writing is done. Red color pen, write down red color pen. Important point. The gradient of angular displacement time graph represents 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 angular velocity. Angular velocity. Angular velocity. Okay. So now we'll draw few theta t graphs and we'll understand what will happen for the gradient, what will happen for the angular velocity of the rotating object. We'll draw three graphs and we'll understand. Okay. Now graph number one for our understanding. If I draw the graph number one, so you also draw with me. So now in graph number one, this is your graph number one. So this blue color line coincides with the x-axis. Huh? So then from this graph, what will be your conclusion? We know if the line is horizontal, gradient 0. Gradient 0 means we know gradient tan theta means delta theta or delta t, that means omega. That means omega angular velocity is 0. That means this graph is applicable for a rotating object at rest. Am I correct? This story. Graph number one, likewise graph number two. You also write down graph number two. Graph number two. So you are getting a graph. You are getting graph like this. Now, because you can argue, because in motion graphs, we learn plenty of graphs. Huh? Here, we don't do so much graphs to understand stories. Here you understand. Here, look here, angle. You know, angle is acute. You can go from back also. Look here, angle is acute. Acute angle means, you know, positive gradient. Right? You can write down acute angle. Angle acute means, you know, gradient, positive gradient. And what can I say about the positive gradient? Positive gradient is constant. When you consider any point on the graph, gradient is constant. Positive gradient constant means positive angular velocity constant, because gradient is angular velocity. Same story. So therefore, this is suitable for a rotating object rotating under constant angular velocity. That means the rotating speed of the object is same. Constant angular velocity. That means speed of the rotating object is same. Graph number two. So we'll do graph number three and we'll talk about angular lost time graph. Graph number three. Graph number three. Graph number 2 done. Graph number 3. So graph number 3, yes. Okay. Graph number 3. Theta. Please refer motion graphs also. Refer motion graph story also. Hands up. Did you get the tutes? Raise your hands. How many of you got the tutes? Hands up. Got the tutes? Hands up. I think you have rotational motion tute. You have, right? You have any? I sent, right? If you didn't receive the tute, let me know. Okay. Now here, this story. The graph is something like this. So what can you do? In this graph, what can you see? When you consider few points, point A, point B, point C, I don't explain like previous stories. Acute angle increases. Don't ask how, we learned. Then here acute angle AA, acute angle increases. Acute means positive. Acute angle is positive gradient. Positive gradient increases. That means positive angular velocity increases. Positive angular velocity increases. That means that rotating object is under angular acceleration. Rotating speed is keep on increasing like a fan. Start slowly, slowly. Got it? Okay. So now put your main topic, angular velocity hyphen time graphs. Angular velocity hyphen time graphs. Omega t graphs. Next story, omega t. Inside the bracket, write an omega t graph. Omega t graphs. Now here also same story. Omega t graphs, you know the story. Now in velocity time graph in linear motion, the gradient of velocity time graph is acceleration, but area under VT graph is displacement. In here also same graphs, only difference is instead of velocity it's angular, instead of displacement it's angular displacement, instead of acceleration it's angular acceleration. Other than that, we are learning the same thing again. That's why we are not learning this again. So if you consider omega t graph, okay, so omega t graph, I draw this graph omega t. Y-axis is angular velocity. What is the unit to measure angular velocity? Rad per second. You need to measure angular velocity rate per second time. Then you are changing y-axis. If you want to find the gradient at a point in the omega t graph, gradient means tan theta. This is delta omega delta t. So therefore gradient in omega t graph, gradient in omega t graph, what? That is alpha. That is alpha, angular acceleration. Same story. Gradient of angular velocity time graph represents angular acceleration. Right? Is angular acceleration. Angular acceleration. Okay. And there's another point. The area under omega t graph, we learned just take a graph like this. So you can take a straight graph or whatever. Okay, I take a graph. There's a graph like this. The area under omega t graph. This area represents Angular displacement. So draw this graph, this story. Don't write one, two, three samples. Huh? This graph, this story, then this graph. Okay, after writing angular acceleration, we'll write a small note. Once you finish doing this graph and this part, please tell me. Raise your hands. We'll write a small point quickly. 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 Now I was saying many times that I will keep an exam, but I could not keep me. Once we finish completing unit 2, rotational motion and circular motion, so we'll have a proper exam paper. Okay, definitely I will, before starting next unit, I will finish everything properly and I will start unit 3. Okay. And also now I have a small plan. Now I am going to start unit 5. I am going to start unit 5 for this 25 batch tomorrow. I will put a message in the group also. Now I noted some teachers what they are doing. Some parts, some new parts not related to unit 2 and unit 3 and unit 4. Some teachers they merge 25 and 26 and they are doing like sometimes in paper class what you do, right? So if you guys now want to cover unit 5 gravitational field earlier, right, gravitational field earlier, what you can do tomorrow, since I'm starting the class tomorrow 6 to 8, 6 p.m. to 8 p.m. We can do gravitational field tomorrow onwards. Every Thursday, every Friday, unit 5 gravitational field. In the March unit 2 completion, in the April unit 3 starting. Likewise, we can do something like that. If not, after a few months later also, we can do unit 5. No issue, but I will put a message in the group and I'll put a poll. Then you just respond how the way that you want. Okay. So I am okay with anything, but just got an idea. Right. So then I think finished writing. Red color pen, write down red color pen, the point, red color pen. The gradient of angular velocity hyphen time graph represents. The gradient of angular velocity hyphen time graph represents. The gradient of angular velocity hyphen time graph represents angular acceleration. Okay, no need, not compulsory, just told. No need then. No need, okay, no need because so much of we are doing many classes, no need. Angular acceleration. So now quickly draw this graph. This one, omega d, this graph. Area under angular velocity time graph. Area under angular velocity time graph. I to this area is capital E. So you guys know that. You guys know that. Area under angular velocity time graph represents angular displacement. So you know that area under angular velocity time graph equals what? Angular displacement. Angular displacement. Angular displacement. That means capital A means, capital A means theta. This story write down. Capital A means theta. No need. Okay, okay, okay. Just that's an idea. Why you guys don't like unit 5? Okay. Okay, we'll do unit 3, 4, and we'll do 5. Okay, no issue. Red color pen write down important. Red color pen write down important. Write down important. What they are telling. So is it only on Friday? Could have joined. No man, no. I I have no time, man. Now Friday also I'm taking revision class time, and I'm doing revision class time bit late, and I'm doing the 25 graduation field. No time ni, because I'm doing two things parallelly. It's very difficult. So you guys don't do two things parallelly. It's not easy as you think. Okay, hereafter only commit to one thing. A level means A level, right? Uh, Other things means other things. If you want to maintain a healthy the thing, A level means A level. Other things mean other things. Definitely, very rarely only you can find people who manage very well in both the things. So therefore, better you focus on A levels, right? Don't do two, three things parallelly. You can't survive. Yeah, you will what get the portion experience, but not in the right level. So therefore, focus on one thing in your life when you are doing in every stage. Okay, right. Okay, done. Red color write down. Red color pen. The area under angular velocity time graph represents the area under angular velocity time graph represents the area under angular velocity time graph represents angular displacement. Angular displacement. Okay. So now take the tute and we'll do tute questions. We'll do tute questions. Mm, we'll do tute questions quickly. Start doing tute questions. Page number 3. Start doing question number 22. Now, no need to go deep. Okay. I think you understood the story. Now you know how to convert a displacement time graph into velocity time graph. You know how to convert VT to ST. And you know if they have a VT graph, you know how to obtain data from that VT graph. You know the story is enough. We are doing angular motion graphs. Question number 22. Start doing 22, 23, and okay, 24. We do these three questions. 22, 23, 24. Not difficult. Start doing 22, 23, 24. Question number 22 says that figure represents a graph which shows the variation of angular velocity time for a rotating object. Okay, calculate the following. You want to find the angular acceleration. Okay, draw the graph. If I draw the graph, y-axis omega, rad per second, rad per second. Your x-axis what? Time. Time measured in seconds. So the graph would be something like this. This is the graph and given data. Now they have given 10, 20, 40. 10, 20, 40 is 0. Now you understand when you consider the motion of this particular rotating object, it follows two types of rotating motions, part 1, part 2. So let's come to part 1, omega t graph, gradient, acute angle means acute angle constant. Acute angle constant means the story. Acute angle constant means it's positive gradient increase, sorry, positive gradient constant. Positive gradient constant means in this scenario, in this motion, positive angular velocity constant. That means that rotating object is rotating under constant rotational speed, constant angular velocity. I made a mistake, okay? So I made a mistake. It's omega t graph. Omega t graph means alpha. Gradient of omega t graph. Gradient of omega t graph is acceleration. Gradient of omega t graph is acceleration. So therefore, acceleration constant, positive acceleration, angular acceleration constant. That means its rotating object is rotating under constant angular acceleration. That means the rotational speed is keep on increasing. In this scenario, you understand, in this scenario, acute angle 0, that means positive gradient 0, that means positive acceleration 0. That means angular acceleration of the object is 0. That means that rotating object is moving under constant angular velocity. That means constant rotational speed. Okay, from that story, we can find simply. We can find simply. Hands up found simple hands. Simply found hands up. Simply found hands up. One done. Simple B found hands up. Simple B. Keep on doing. Now can do. Now can do. Keep on doing. Simply. Always think this is a VT graph. Then story finished. VT graph. If you want to find the acceleration, this part belongs to acceleration. Then VT graph acceleration means the gradient. Omega t graph angular velocity time graph acceleration means the gradient. That means tan theta. Sorry, tan theta, tan alpha, whatever. This angle is let's say theta. Tan theta means what? If you consider this point as point capital O, this point is point capital O, point capital A, this point is point capital B. So you can take OB right angle triangle if you want. If you want, you can take OB right angle triangle. This is 10, this is 10, this is 20. Right? So therefore, angular acceleration means alpha means we know alpha means in omega t graph, alpha means the gradient. Gradient means tan theta. Gradient means tan theta. Tan theta means we know opposite is how much tan theta. Opposite is this opposite how much? Opposite is 20. Adjacent 10. 20 over 10. 20 over 10. That means 2 rad per square second. Alpha. Not difficult. Then what? Simple alpha angular acceleration I found. Then simple B they are asking what? Simple B they are asking the total angle it rotates during 40 seconds. During 40 seconds means within the entire time the total angular displacement omega t graph area represents angular displacement. Omega t graph area represents angular displacement. If you can find the entire area, that will be the total angular displacement. Okay. So therefore, total angular displacement theta t means the area. Triangular area half Base is how much? 10. Height is 20. Rectangular area. Yeah, it's 10. 10 to 30 means this gap is how much? This gap is 30. This height is 20. 30 into 20. 30 into 20. This story. We learned these stories in the beginning of the classes. Then here we can write down here. We can write down here. Here this is 5. 20 into 5 means 100. 30 into 200 means how much? 600. 600 plus 100 means 700. Rat. Rat. T. Hands up who finished doing question number 22. Hands up. 22 done. Hands up. 22 done. Hands up. Question number 22 done. Hands up. Still doing answer? Still doing? We learned the stories, huh? Then C part is easy. It mean angular velocity means, mean angular velocity means average angular velocity. Lastly, we learned average angular velocity means when you divide total angular displacement. When you divide total angular displacement by total time, that is the average angular velocity, mean angular velocity. It's not difficult. C. Part C. So you know average angular velocity, the equation. Average angular velocity means we know total angular displacement. Total angular displacement that over tt. Total angular displacement that over tt. Total time. Total angular displacement within 40 seconds, I found 700. Over total time is 40 seconds. Here 70 over 4 means 35 over 2 means 17.5 rad per second. Rad per second. Average. 22 done, 23, 24. Start doing 23. Not difficult. 23, can do. If I do the graph, 23 graph. 23rd one. If you do the graph, free rotating wheel stops its motion after the gradual decrement of its speed. Speed means rotational speed. Huh? Gradual decrement of its speed under the influence of an external torque with a time period of 20 seconds. You know what is torque? Sometimes you are not very familiar. Based on the direction of torque, what will happen for the rotational speed? What will happen for the angular velocity? Sometimes you are not very familiar. You know what is torque? The reason behind object's rotation is torque, right? When you provide the torque in the direction of rotation, what will now we will learn this story now. Just think about forces. Now there's an object under motion to the right side direction. An object under motion to the right side direction. When you apply a force in the direction of motion, velocity increases, undergoes acceleration in that direction. If you apply the force in the opposite direction of motion, and velocity decreases, undergoes deceleration in that direction. Now, same stories in torque also. The reason behind rotational motion is torque. If you apply the torque in the direction of rotation, angular velocity increases, undergoes angular acceleration. If you apply a torque in the opposite direction of rotation, now disk is rotating clockwise, you are applying the torque in the anti-clockwise direction. Then angular velocity decreases, undergoes angular deceleration. The same story, you don't need to worry what's happening there. Only data is important. 20 seconds. Okay. Right. We want to find the angular deceleration. Then angle, same story, not difficult. Same story, not difficult. Hands up who finished 23 hands up. 23 hands up, finished. 23 finished. No one yet. Then omega. Okay, omega t graph. Given data 10, 10, 30. 10, 10, 30. First, now you know here the story. We know angular velocity is constant. Look at the y-axis. You can argue like this also. Now here on any from 30 second to sorry from 10 second to 30 second only, what will happen for the angular velocity? It decreases. So therefore you can say this is the deceleration, angular deceleration, constant angular velocity motion, angular deceleration. First they are asking angular deceleration. First they are asking angular deceleration. Not difficult. Not difficult. Simple A. If you put this as the theta, tan theta means ni angular deceleration means how much? Tan theta. Tan theta means we know opposite over adjacent. Opposite is 10. Adjacent is how much? 10, this gap is 20. 10 to 30 means 20. So therefore, angular deceleration of the motion is how much? 0.5. 0.5 rad per square second. So then they are asking total angular displacement simple B. Total angular displacement simple B. What? That is the total area. So rectangle plus triangle. The rectangle plus triangle. The rectangle area. So we know this gap is 10. This gap unit is 10. Then theta t total means what? Not difficult. Theta t total means we know 10 into 10 means 100 plus this area means half, base 20, height is 10. Then 200 means this is also 100. 100 plus 100 is 200. 200 rats. Are this difficult? These are not difficult stories. If you properly learn motion graphs, because I think online people have the access to, no, you can, now hands up, you have the access to recordings. All the previous recordings you have access, right? Hands up, online people. You have any? So then if you want, you can refer it. But I know that some people you give access to your friends and you are watching the recordings. You are letting them to watch the recordings. Not you guys. Just I'm telling some people they do like that. But I don't say anything for that. Nee, right. Okay, shall we do the last one? Last one, we'll talk about what is that moment of inertia, the very important part in rotational motion. Moment of inertia. The last part. Hands up who started doing the question number 24, hands up. Started doing 24, hands up. 24 started. Good.
So I also do 24. Then okay, I will do 24. In 24 story, question number 24. In 24, if I do the graph, y-axis represents what? That is also omega t graph, ne? Omega. That is also omega. Time graph, ne? Okay. And then the graph would be like this, ne? This is the graph. And they have given these values: -4, 10, 25, 6. -4, 10, 25. This gap is 6. Omega measured in rad per second. Time measured in seconds. What they are asking in the beginning, find acceleration of the object. Acceleration. So tan theta only. So you know that any point acute angle constant. Am I correct? Acute angle constant means positive gradient constant. Now omega t graph gradient is acceleration, positive acceleration constant. That means angular acceleration is constant. Story. So what you can do here, you can go with different ways. You can use y2 minus y1 over x2 minus x1. If not, you can find this length. If you can find this length also fine. If you can find this length also, it would be fine. It's up to you. How many of you went with y2 minus y1 over x2 minus x1 answer? How many of you went with y2 minus y1 over x2 minus x1 answer? How? Many. So therefore, I'm also going in that way. If not, you know this length you can do it. So I'm also going with y2 minus y1 over x2 minus x1. Then we know that tan theta. Alpha means tan theta. That means y2 minus y1 over x2 minus x1. x2 minus x1. So who is my y2 x2 y1 x1? Now this one will be my x1 y1. What is the coordinates of this point? This point coordinate x value is 0, y value is -4. Coordinates of you can take this point coordinate also if you want. If not, you can take these 2 points in. It's up to you. This point coordinate is what? X value is 10, y value is 0. This point coordinate, you can take what? You can take it as 25 x value, 6 y value. So I will take these 2 points. If not, you can take these 2 points. It's up to you. If not, you can take these 2 points. You will get, if not, you can take these 2 points. No matter whatever the 2 points you take, you will get the same answer. So then y2, I take this as my x2, y2. This is x1. This is y1. So alpha means we know that y2 means 6 minus y1 means 0 over x2 means 25. 25 minus x1 is 10. That means 6 over 25 minus 10 means 15. Hands up who got 6 or 15 hands up. 6 or 15 means 2 over 5, 0.4. Hands up who got 0.4 hands up. 0.5. Now see the same story. Now you understand now what is the pattern of rotational motion. Right? A comparison. You should have a comparison. Then the story is easy. Okay? Always compare. Now see, did we learn anything new actually? Centripetal acceleration is somewhat new. Tangential acceleration. That story, this part is bit new. But other than the remaining same story, we are doing again and again, right? Same story. Same story. So then 0.4 rad per square second, 0.4. And also we'll find what is this, we'll find the simple B part, then story finished. Simple B part. They are asking total angular displacement. What they are telling? What is the total angle if rotated within the time period 25 seconds? 25 second time period total angle. First of all, find the, we know omega t graph, uh, area represents angular displacement theta. Area represents angular displacement theta. Okay. What is the area of this triangle? The area of this triangle will be, you know that, base 10, this gap is 4. Half 10 into 4. Then you are getting how much? 20 rad. This angle, area under this triangle is 20 rad. This one angle, this one area, sorry, this one area, 15, height is 6. Then what is the equation? The equation is half base 15, height 6, 45. Now you might have a problem, sir. Now, hands up. How many of you got the answer? How many of you got the answer for this simple B part? 25 rad hands up. How many of you got the answer for simple B part? 25 rad hands up. 25 rad. Anyone? Anyone? No one got 25 rad. I think you all got 65 rad. Why? Because I told you in the beginning of rotational motion, angular displacement is a scalar. Angular displacement is a scalar. Keep that in your mind. But in linear motion, displacement is a vector. If this is rather than omega t, if it is vt, if you want to find the total displacement, this area should be subtracted from this area. But they are asking total angle. Angular displacement is an angle which is a scalar. So therefore, find the area separately 20, that area separately 45, 20 plus 40 was 65. Story finished. Story finished. I think we started the class exactly at 2:30. I would start at 2 o'clock because my charge went off and waiting to this to charge. Crystal clear and sub. Story, yes, everything very clear. Everything is crystal clear and sub. Story is very, very clear. Okay. So then, right now you know that. Now just compare. If you have a linear motion to notes, please. After we discussed about distance, displacement, velocity, acceleration, speed, then we talked about linear motion equations. Then we talked about vertical motion, projectile motion, but in rotational motion, we are not talking anything something like that. Vertical motion, rotational motion, we are not talking in in rotational motion. Then after in linear motion, vertical motion, or projectile motion, then motion graphs. Now rotational motion. Now we talked about angular motion graphs, rotational motion graphs. Now in linear motion, after discussing motion graphs, we talked about inertia, I think force, Newton laws. if not linear momentum. Now we are talking something related to that. So put your main topic. So we'll take a break at now. Time is 3:45. Need a break answer. Need a break answer. So we started at 2:30 and 3:33. I thought of giving the break at 4:15. No, not 4:15. 2:30, 3:30, 4:30. I thought to give the break at 4:45. After 1 hour only, I will give the break. You need the break now, hands? Let's take a break and come, hands. No need, right? No need. But what I do, but this is not a break. This seem like a break, right? You ask me it's not a break. What you do, you just stay 5 minutes. If you want, you drink and come 5 minutes. Okay, it's not a break. I assume it's just a not a break. Now 3:46. I start at 3:51. It's not a break. 3:51. Yes. Yes. Right. So now what shall we do now? We'll put the next graph. I don't do anything in that graph part. So you know how to convert omega t to theta t, how to convert theta t to omega t. You know the stories, not that much different. So we have done few questions. Story is finished. We are not going to do anything in the theory class. This is the way, right? So now what you do, the last part, put your topic, last graph, put your topic, angular acceleration time graph, alpha t graph. So we talk only about the gradient. Sorry, we talk only about the area under alpha t graph. If you can remember acceleration time graph, the area under acceleration time graph represents velocity. So likewise, when you consider, if you draw a graph, angular acceleration time graph, alpha t graph, area under alpha t graph represents what? Angular velocity. First of all draw alpha t graph, angular acceleration hyphen time graph. So you don't write alpha t, you write first angular acceleration with your words, angular acceleration hyphen time graph, inside the bracket alpha t graph. Draw this diagram. This diagram, area under alpha t graph, angular velocity, angular velocity. If you finish writing, raise your hands. Up to here. Once you finish writing up to here, raise your hands and put your okay. Raise your hands. Don't put any topic. Up to here, write. Once you finish, hands up. Once you finish, hands up. The topic is angular acceleration hyphen time graph. So we discussed angular displacement time graph, angular velocity time graph. Now we'll talk about angular acceleration hyphen time graph. So this diagram again, this one again, this part. Then stop writing. Then stop writing. Once you finish, raise your hands. Once you finished, raise your hands. Red color and white on a point. The area under angular acceleration time graph. The area under angular acceleration time graph. The area under angular acceleration time graph represents angular velocity. Represents angular velocity. Represents angular velocity. Now main topic. Put your main topic. So now time is almost 4 o'clock. You are going to stay with me maximum. You are going to stay with me for maximum. How long? 6, 6, 5, 16 only. Okay. So you are going to stay with me for maximum 2 hours. 2 hours. Okay. Right on main topic. Main topic. Mm, rotational inertia hyphen no slash rotational inertia slash moment of inertia. Rotational inertia slash moment of inertia. Inside the bracket, capital I, close the bracket. Okay. Now look here. Right now, in linear motion also we talked about inertia. Can you remember what is the important points there we learned? Inertia means we know the reluctance, the resistance to change an object's current state of motion. For example, if an object is at rest, it does not like to move because its current state of motion is at rest. So that object doesn't like to move. That object doesn't like to change its current state of motion. And also we can apply, just think about an object moving. That object doesn't like to change its velocity. If that object is moving under same velocity, for an example 50 ms minus 1 right side direction, that object doesn't like to change that velocity. So there is kind of reluctance, resistance in object's end to change its state of motion current. So this is what we defined as inertia, right? So then we realized when we were learning those stories, if we want to change an object's current state of motion, there should be an involvement of external something. That something we named as force. And also we know inertia depends on the mass. Large the mass, large the reluctance. The story is very simple. Inertia means an object. Inertia means resistance or reluctance to change an object's current state of motion. If the mass of the object is greater, the inertia shown by that object is also greater. I compare two masses. Just consider 5 grams spear and 5-ton huge spherical rock. Initially, both of them are at rest. If you want to move them now, therefore, definitely you want to change their current state of motion. Am I correct? Initially, there are two masses, 5 gram and 5 ton. If you want to change their current state of motion, means if you want to move them, means definitely you should apply an external force. Since the mass of larger rock is larger, that larger rock shows larger resistance to change. Now you start applying the external force for both the small 5 gram mass and 5 ton mass. You are start applying the force gradually. You are starting from zero, right? So 1 Newton you applied for both the rocks, both the masses. Then 1 Newton, 2 Newton, 3 Newton. But when you apply 5 Newton force, that smaller mass object could easily move. We could easily change small objects' current state of motion easily. But the problem is when it comes to the larger rock, even you apply 5 Newton, even you apply 100,000 Newtons, it's not easy. If you want to change, because the reluctance is high. So therefore, you want to apply a large force. When you apply a force 10,000 Newton, then maybe that object starts moving. That object can change state of motion. Summary very simple. Summary is, you know what is inertia? Reluctance. Inertia depends on mass. Larger mass, larger inertia. If you want to change larger mass state of motion, you want to apply larger force. Larger mass means large inertia. The required external force also large. That story there. Not only this is applicable for linear motion, But keep in your mind, this is applicable for rotational motion also. Okay. So now we know that. Just consider any rotating object in our day-to-day life. The best example is a fan, right? So always we see in our home a rotation of a fan. If not, what else you see in your home rotational motion? Give me some examples. If you girls, I know that you girls go to the kitchen, you girls support your parents. Definitely you support your mother when she cooks. Then you might have seen there is a device in your kitchen called blender. Raise your hands. How many of you aware about blenders? Hands up. You guys know blenders. That means you guys have gone to kitchen. That's a very big thing. Yes, very good. Now generation that girls going to kitchen means a really appreciating thing. Very good. In that blenders, that blender blade is undergoing rotation. What else? Give me some examples since you aware those stories. Give some examples rotational motion in happening in the home. Can you give some examples? Give me some examples. Give me some examples. Amaya, I think you know that you are going to kitchen daily, not to eat, but to help your mother and father. A father is not going to kitchen, only mother. Ni. So can you give me some one example? Yes, Malki, I think in your home in your home kitchen also there's a fan, right? I think okay, very good. And electric coconut scrape. Oh God. Oh, very good, very good. Great. Electric coconut scrape. That means that thing, sir. Yes, I know. පොල්ගාන මැශිම නේද? අර ඉස්සර අපි පාවිච්චි කරේ හිරමනේ නේද සිංහලෙන් කියන්නේ? Now electric. Now day by day work is getting easy. Now girls don't want to do anything in the kitchen. They just want to switch on all the things. When they switch on, everything will happen. That's really good, right? It's really good. Okay. So okay, now then what I want to say is when you consider any rotating object, they all rotated in a certain axis. Am I correct? All the rotating objects rotate in a certain axis. So therefore, rotational objects also, there is a reluctance to change their current state of motion. For an example, just think when the fan is switched off. Fan is switched off. If the fan is not rotating, and when you switch on, some people see kind of very high force. Fan starts to shake. If not, you might have observed now. Fan is initially off. When you suddenly switch on the fan, you might have seen kind of a quick shock happening in the fan to start moving, right? So therefore, fan at rest doesn't like to rotate. Fan which is rotating, let's say now your fan is rotating at speed 5, speed in the regulator. When you turn into speed 5, now your fan is rotating with speed 5. Suddenly you stop the fan. Suddenly when you stop the fan, will the fan come quickly at rest? That instantly the fan come at rest? No, right? Because fan like to keep on rotating. Fan doesn't like to come at rest quickly. When you consider any rotating object, they don't like to change their current state of rotational motion. So this is what we call as rotational inertia. See, now you understand something very similar, right? Everything that we link with the linear motion. If you understand the stories in linear motion, the story is not difficult. So write down different color pen, write down. Different color pen, write down. We'll take a break at 4:45. Okay. Write down. Different color pen. The reluctance shown by an object. The reluctance shown by an object to change its nature of rotational motion. To change its nature of rotational motion. About a given axis. About a given axis. About a given axis. Normal pen write down. Is known as is known as moment of inertia slash rotational inertia. Is known as moment of inertia slash rotational inertia. Right? Okay. The next point write down. That means when you're writing, understand, write down. That means the reluctance of a stationary object to rotate. The reluctance of a stationary object to rotate, or or of a rotating object to remain stationary, or a rotating object to return to stationary. A rotating object to return to stationary. A rotating object to return to stationary is called as moment of inertia. I think I don't need to explain them, right? Now, anyhow, finally, you know that rotational objects also have kind of inertia. The resistance to change their current state of rotational motion is what we call as inertia. Moment of inertia, if not rotational inertia. Now, this rotational inertia depends on few factors. So, write down a topic write down factors on which moment of inertia depends. Factors on which moment of inertia depends. Factors on which moment of inertia depends. Number one, write down number one, mass. Number one, write down mass. Okay, this is important story. Hereafter, all the story is important. Number one, mass. Keep your focus until 4:45. Right, we'll take a break then. Number one, moment of inertia depends on mass. Right. So now keep in your mind there is a direct proportionality between moment of inertia and mass. In linear motion also inertia depends on the mass. Large the mass, large the inertia. In rotational motion also moment of inertia, if not rotational inertia, depends on the mass. Large the mass, keep in your mind, large the moment of inertia. Rotational inertia is larger. So write down below the relationship. Moment of inertia is directly proportional to mass, proportionally 1. Moment of inertia directly proportional to mass, proportionally 1. Okay, right. Number two, now these things you're not very familiar. Number two, distance measured from the rotational axis. If not distance from the rotational axis, distance from the rotational axis. Now I will show a diagram and I will make you understand. Now the best example is, let's consider a circular disc. I try to draw a 3D circular disc. We'll try it. A circular disc. If not just think a circular cylinder. A circular cylinder. Right? A circular cylinder. If I mark now rotational axis, I'll mark rotational axis. This would be the rotational axis. Okay. I say the axis of the rotating in this direction. Then it's a solid cylinder. It's a solid cylinder. Now this moment of inertia depends on the distance from the axis of rotation. So you can tell now when you consider this mass, now this material has spread throughout this region, right? Evenly, this material has spread throughout this region, this cylinder. When you consider this solid cylinder, material has spread throughout this region evenly spread. So then, what is the largest distance to the particle? When you consider material particles, what is the largest distance to the particle from the axis of rotation? Now you know particles are everywhere. What is the largest distance to the particle from the axis of rotation? So you will mark. So this particle, if the particles at this circular circumference, am I correct? The particles at circular circumference has the largest distance from the axis, right? The particles at the circumference have the largest distance from the axis. So therefore, so the distance to the particle which is at the largest distance from the axis, that distance I mark it as simple r. Simple r. Right? So keep in your mind, moment of inertia depends on simple r. The relationship is directly proportional to distance squared. So draw this diagram. Simple r, mark simple r. Then this proportionality. Moment of inertia, rotational inertia depends on r squared, equation 2. Write down. Write quickly. So now I think you wrote like this thing. Okay, look here. You wrote distance from the rotational axis to the mass distribution, right? Like this. Number two, a distance from the rotational axis to the mass distribution. To the mass distribution. I forgot to tell you guys to highlight in that definition, rotation inertia. You wrote in different color pen definition. In that definition, please highlight about a given axis. About a given axis, because you will understand when the axis is different, your rotational inertia is completely going to different. So therefore, about a given axis highlight. So now we are talking about the factors which depend on rotational moment of inertia. Number one is mass. Number two is distance from the rotational axis to the mass distribution. To the mass distribution, this diagram, these two proportionalities. Complete quickly. So then you can write down. Now in linear motion, we didn't write any equation for moment of inertia, right? Sorry, inertia. In linear motion, we didn't write any equation to the inertia. We just told that inertia depends on the mass. Larger mass means larger inertia. In that case, we require larger force to change that object's current state of motion. But in rotational motion, We defined what is rotational inertia, if not moment of inertia. Now we are going to derive an equation, general equation for moment of inertia, and we talk about moment of inertia of different objects with different shapes. So we learn this moment of inertia a bit deep in here. Okay. So from proportionally 1 and 2, we can write down, keep your focus. We can write down a moment of inertia directly proportional to what? Mass into r squared. Am I correct? So to remove this proportionality, we are using a constant I equals, that constant I mark it as k. K mr squared. K is a constant. This depends on the material, maybe this depends on the shape of the object. This depends on the different factors. Okay, K equals mr squared. Highlight this equation. Highlight this equation. Mr squared, a constant. This equation highlight. 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 Now write down, please highlight this equation also. I equals k mr squared. K is a constant. Write down k is a constant. K is a constant. Write down k is a constant, which depends on the shape, 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 and the rotational axis of the object. And the rotational axis of the object. Highlight shape, rotational axis. Highlight shape, rotational axis. Okay, right. Quickly find the units of moment of inertia, dimensions of moment of inertia. Find them. Find them. Okay, find them. And also write down, this constant does not have any units. Huh? This constant does not have any units. Write down this constant, k does not have any units. What is the units of moment of inertia? Units of phi. Uh, k does not have any units. Mass measured in kilograms. Uh, Radius, sorry, distance means measured in meters. Kgm squared. Kgm squared. Dimensions of moment of inertia. Dimensions of mass. Dimensions of distance squared. Capital M. L squared means ml squared. ml squared. Nee. Now, slowly, little by little, I'm teaching all the points. You gain those things and think, imagine. Red color pen, moment of inertia is a scalar. Red color pen, moment of inertia is scalar. Scalar, units, dimensions, everything is okay. Now, super red color pen, write down. Now, up to now, when you compare rotational motion and linear motion, uh, they were quite similar. Okay. How, to whom we did the comparison? We did the comparison for angular displacement with displacement in linear motion. Angular displacement is an angle, theta. Displacement means distance, capital S. They were somewhat similar. And we compared in rotational motion angular velocity with velocity in linear motion. They are somewhat similar. Linear speed is velocity, rotational speed is angular velocity. Story okay. And then we compared angular acceleration with linear acceleration A. They are not exactly same, but somewhat similar ideas. But hereafter, keep in your mind, hereafter, now we talked about moment of inertia. And the general equation of moment of inertia of an object is k m r squared. K depends on the shape and the axis. Remember, whatever the physical quantity we identify in linear motion as mass, simple m, when it comes to rotational motion, we identify as capital I, moment of inertia. Do you understand? Now you don't ask why, how. I also no, there is no answer. There's no answer for that. Now, whatever the physical quantity we identify as mass in linear motion, when it comes to rotational motion, we identify as moment of inertia I. Super red color pen, write down. Take a super red color pen, write down, write down. Super red color pen, very important point. Write down. Whatever the physical quantity, sorry, write this. The physical quantity known as mass in linear motion, the physical quantity known as mass in linear motion is identified as the moment of inertia, is identified as the moment of inertia in angular motion, in rotational motion, in angular motion, is known as the moment of inertia in angular motion. Now hereafter, when it comes to rotational motion, always think simple m means I. Yeah? In the beginning, sometimes you might feel very unfamiliar with the practice, with the questions you understand. Write down number one. Number one, moment of inertia about a point mass. Moment of inertia about a point mass. Number one, moment of inertia about a point mass. Look here, write down. Under that, write down. Under that, write down. Under that, moment of inertia about a point mass. Under that, write down. The moment of inertia of a point mass simple limb. The moment of inertia of a point mass simple limb. The moment of inertia of a point mass simple limb rotating in a circle of radius simple r, rotating in a circle of radius simple r, can be expressed as below, can be expressed as below, can be expressed as below. Look here. If I repeat it again, uh, I told what? I told the moment of inertia about point mass is your topic. Moment of inertia about point mass is your topic. Moment of inertia of a point mass simple limb rotating in a circle of radius simple r, rotating in a circle of radius simple r, can be expressed as below, can be expressed as below, right? Okay. Now this diagram, now there is a small point mass rotating in a circle of radius simple r, right? From the point of rotation, This is the radius simple r. If I mark the point mass simple limb, it's rotating in clockwise or anti-clockwise. It's up to you. Rotating in clockwise or anti-clockwise, it's up to you. So if you want to find the moment of inertia of simple limb point mass, the equation will be I equals mr square. The equation will be I equals mr squared. Then you might ask, what is the value of k? I told you k depends on the shape and axis of the object. So now when it comes to a point mass, what will be the k value? K is 1. Okay, this equation highlight. You must learn by heart. In exam MCQs, they don't give, they tell there's a point mass undergoing rotational motion. Then you should know if it is a point mass rotating, moment of inertia will be mr squared. Therefore, learn by heart this equation. Hereafter, you want to learn by heart these equations. Huh? Learn by heart. Quickly. Then write on k is 1. In here, k is 1. K is 1. This is first story. Finish, stands up. If you finish, stands up. Last 15 minutes for the break. Done. Next what? Number 2. Now this is a point mass. What about a evenly mass distributed rod? A thin rod. Its mass is evenly distributed. And when you consider your axis passing through the midpoint of the rod, how would be the moment of inertia? Write down. Number 2, moment of inertia of a uniform thin rod. Moment of inertia of a uniform thin rod of mass capital M. Uniform thin rod of mass capital M. And length capital L. And length capital L. About an axis. About an axis. Which goes through the midpoint of the rod. Which goes through the midpoint of the rod. Which goes through the midpoint of the rod. Midpoint of the rod. Okay, number 2. Number 2, now highlight the thin and uniform. Highlight thin and uniform because those are important conditions. That's a rod. Okay. Length of the rod is capital L. length is capital L, mass of the rod is capital M, mass capital M. Now this rod is now you think this is my rod. Wait a second. This is the rod. I can make this rod rotating in different axes. Okay. Now see. Now see. Can't see any. Right? If you can understand what I'm doing, right? I want to repeat it. Wait. Can see. Can see. What is can see? What do you mean by can see? Uh, just for a reply. What do you mean by can see? So now you understand. Now here, now this rod is rotating about an axis passing to midpoint. Just think a vertical line. The vertical line passing to the midpoint of the rod. The vertical line passing the midpoint of the rod. This rod is rotating about this axis. This is one way of rotation of the rod. Second way is, this is your rod. Consider an axis passing vertically through one of the ends. This is your axis of rotation. Then this is your axis. Think this finger is your axis of rotation. This axis is passing through one of the ends of the rod. Then how would the rotation? Oh God. Do you understand? Right, there is another one. There's another one. I will say the sentence again. Don't worry. Okay, I'll say the sentence again. That's another rotation. Now think about an axis passing through this circular cross-sectional area center. If your axis is passing through the center of the circular cross-section of this rod, the rotation will be like this. So therefore, you understand there are different possible rotations when the axis is different. Based on the axis, keep in your mind, the moment of inertia is different. That means the reluctance, the resistance to change the rotational motion is different. Keep in your mind the idea. Depends on the axis, depends on the mass, depends on the distance, simple R. Keep in your mind, moment of inertia. Reluctance to change rotational motion is going different. This is your story. Now, if I consider, now I told the sentence, if I repeat the sentence will be something like the sentence write down. Moment of inertia of a uniform thin rod. Moment of inertia of a uniform thin rod of mass capital M and length capital L. Of mass capital M and length capital L about an axis. About an axis which goes through the midpoint of the rod. Which goes through the midpoint of the rod. Midpoint of the rod. Okay, right? Now this time the axis of rotation is passing through the midpoint of the rod. What is the midpoint? Total length is capital L. Uniform thin rod. Midpoint is L by 2. From the end, L by 2. This is the midpoint. Okay. This is the axis. Axis of rotation. Then this gap will be, it's L by 2. Am I correct? L by 2. The equation to find the moment of inertia will be keep in your mind in this scenario. I equals, I think it's 1 over 12. I equals 1 over 12 ml squared. Yes. I equals 1 over 12 ml squared. Now you understand, right? The general equation MR, mass distance squared, same story, but depends on the geometry of the rod, depends on the axis, what will happen? The constant is varying. Highlight this equation also. This equation highlight. Number two, once you finish, hands up. So within 8 minutes, we'll take a break. Once you finish, hands up. Once you finish, raise your hands. So how did you get 1 over 12? That is also, we want to derive it. It's a big part that is not belong to you. It's a big part actually. Derivation that 1 over 12 came, it want to do derive it. Can get it. We want to use so many math stuffs. Okay. Now you know that you get you will learn, I think, in if you are doing maths, you will learn what is the equation to find the volume of a sphere. 4 over 3 phi r cube. What is the equation to find the volume of a what cylinder? 2 phi r h. In if you are doing maths, when you are doing differentiation and integration, when you are doing integration, you will derive those equations using integration. Likewise, here also you can derive these things, but not in your syllabus and don't want to know those things also. Right? Okay. Okay. Right. If you finished, hands up. Finished, hands up. Number three, write down then. Number three, write down. Uniform moment of, write down, same story. Moment of inertia of a uniform thin rod of mass capital M, same story. Moment of inertia of a uniform thin rod of mass capital M. And length capital L. And length capital L. About an axis. About an axis. Which goes through the which goes through the one of the ends of the rod. One of the ends of the rod. This time your axis of rotation is through the one of the ends of the rod. I'll ask the question. Now look here. If I ask you a question, you can take whatever the way that you like. Length, mass, capital M. Length is what? Length is capital L. And this capital L. Uh, my question is, now they have given two rods, same mass, same length, identical two rods. Student A is, one student is rotating the rod about an axis passing to the midpoint. Another student is rotating the rod about an axis passing through the one of the ends of the rod. My question is, which motion has the largest moment of inertia? In which case, when you try to rotate in the beginning, when you start to rotate, in which case the rotational inertia is high, which case you want to put a larger effort. In the beginning, both are at rest. You want to rotate both of them. Their axis of rotation is different. If you are going to rotate both of them, In which rot in the beginning you want to put a larger effort. If you are putting a large effort means larger moment of inertia belongs to which rot. Raise your hands. How many of you say option one answer, first one answer? The largest effort I want to put for rod one answer with the practice answer. First one answer. Second one answer, second one answer, second one. Second one answer, second one. So the effort that you want to put is larger in second one than the first one. Right? When the mass now see I told you normally the thumb of rule is from the axis mass distribution is large means the thumb rule is from the axis of rotation mass distribution is larger means large moment of inertia difficult to rotate reluctance is high. Now I taught you how to find the mass distribution length in this rod from this axis. What is the largest distance to the last particle of the rod? If you measure from this axis, the largest distance belongs to this particle at the end, right? That distance is L over 2. But in this scenario, from this axis, the largest distance to the last particle is L. This is larger. Larger mass distribution means larger moment of inertia, larger torque required. You'll understand why torque required. You'll understand large amount of inertia, large effort. So now, if you know this equation, if you know this equation, you can derive this equation. The equation is 1 over 3 ml square. Write down. In this case, the equation will be I equals 1 over 3 ml square. I equals 1 over 3 ml square. Now I will give a homework. Okay. I'm not going to do it, but when I do one sample question, I think you'll be able to do it. I think. Uh, okay, it's okay. Okay, in the sample question, you understand if they have given this equation, how to derive this equation, you can do it. Okay, right now just write down 1 over 3. Now see 1 over 2 means small, 1 over 3 means bit large, large amount of inertia. What is the time now? Interval time. Is the interval time? Yes, 4:45. How long you want? I think continuously we learned, I think from 2:30 to 35, 23, 4:35 for around more than 2 hours. We continuously we learned. Only we took a small 5 minute break because I'm tired only. Reply everyone in the chat box. I think up to now story is very clear answer. Yes, everything is very clear answer. Story is crystal clear answer. No issues so far. How long you want? Put in the reply chat box. How long you want? I'm doing the class until 6 o'clock. Reply how long you want, everyone. Put Malki how long you want. Everyone put how long you guys want. Malki is not responding. So we'll take 15-minute break. Sometimes I might take 20-minute break. Okay, we'll come at 5. Sometimes I might come at 5. Okay, take a break and come. Wash your face, eat something and come.
Yes, we are back. So you're going to stay with me for last maximum 1 hour. Okay. So I think 2 and 3 done. We'll go to next one. Then fourth one. Now we'll talk about then what would be the moment of inertia equation for a rotating thin disk in the circular shape one. Write down. Write down. Write down. Moment of inertia of a uniform thin circular disk. Moment of inertia of a uniform thin circular disk. Uniform thin circular disk of mass capital M and radius capital R. Of mass capital M and radius capital R about an axis about an axis which goes through the center of the disk, which goes through the center of the disk. Which goes through the center of the disk. Right? Okay. Okay. So now the next story is not difficult. Now, if it's a disk, now next one is if it's a disk of radius, a very thin disk, a circular shape, very thin disk, radius capital R, mass capital M. If you want to find the moment of inertia, it's a very thin disk. Okay, very thin disk. Huh? Then the equation will be the axis of rotation will be the axis passing through the center of the disk. This is the axis. Equation will be I equals what? Half mr square. I equals half m r squared. I equals half mr squared. Highlight this equation. Next one. Next one, fifth one. Right, finished. If I repeat it again, uh, now the moment of inertia of a uniform thin disk of mass capital M and radius capital R about an axis which goes through the center of the disk. Now you can match it now. From the previous sentence, you can match the what is the main difference? What is the difference between this to that? Hands up, finished hands up. Finished hands up. Finished hands up. Okay, now next one you write the sentence. I don't want to tell right momentum now. If I'm talking about solid cylinder, if I talk about solid cylinder of radius capital R and mass capital M, what you want to do? Moment of inertia of a solid cylinder of radius capital R and mass capital M about an axis passing through the center. Right. So you can write right.
So next one is solid cylinder. Solid cylinder, next one. So you write the sentence. If I draw the diagram, if I draw the diagram, this is the axis of rotation. Axis passing to the center of the solid cylinder. This is the axis. Axis of rotation. Radius given as capital R is the radius capital R. Mass capital M mass. Radius capital R, mass capital M. Then the equation of moment of inertia will be what? 1 over 2 mr squared. Moment of inertia 1 over 2. Same. Disk moment of inertia and solid cylinder of radius capital R. It doesn't matter what is the length. It doesn't matter about the length of the cylinder. It only depends on the radius. Okay, from the axis to the last mass particle. From the axis to the last particle. So then 1 over 2 mr squared. I equals half mr squared. I equals half mr squared equation. So when you're writing moment of inertia of a solid cylinder of mass capital M and radius capital R about an axis passing to the center, you can write down, right? So next one, sixth one. Next one, moment of inertia of a solid sphere. Moment of next one we'll write down hollow cylinder. Hollow cylinder. Moment of inertia of a hollow cylinder. Moment of inertia of a hollow cylinder. So when you're writing now this one, moment of inertia of a hollow thin cylinder. Hollow thin cylinder. Okay. Moment of inertia of a hollow thin cylinder. Radius capital R, mass capital M. Radius capital R, mass capital M. Now, when you're writing here, write down moment of inertia of a hollow thin highlight thin cylinder of mass capital M and radius capital R about an axis passing to the center. About an axis passing to the center. This equation also capital M capital R square, mr square. I equals mr square. I equals mr square equation. Okay. Next one. I equals mr square. Next one. Next one, moment of inertia of a solid sphere. Moment of inertia of a solid sphere. The next one, solid sphere. Now I can draw a circle, but you won't imagine this is not a circle, it's a sphere. Its radius capital R, mass capital M. Then we can write a moment of inertia as what? I equals, this is also I think 2 over 5 mr squared. 2 over 5 mr squared. So you must learn by heart these equations, okay? So when you are preparing a short note, include these things. The last one is hollow, now solid sphere, hollow sphere. Hollow sphere, now when you're writing moment of inertia for hollow sphere with thin moment of inertia of a thin hollow sphere of radius capital R and mass capital M about an axis passing the center. So write like that. The last one is eighth one is hollow sphere. Okay, very thin hollow sphere. Now mark draw this as very thin. Na? Radius capital R, mass capital M. In this case, the equation will be 2 over 3 mr square. I equals 2 over 3 capital M capital R squared equation. Right. Right. If you finished, hands up. If you finished, hands up. Once you finish writing, raise your hands. Now we'll do one more theory part and then we can discuss. Once you finish doing this, we can discuss about the questions related to amount of inertia. Okay, quickly do it. Do it quickly. Once you finish, raise your hands. Once you finish, raise your hands. Seventh one. What is the seventh one? Seventh one is solid sphere. This is solid sphere. Moment of inertia of a solid sphere of radius capital R and mass capital M about an axis passing to the center. Center. So mostly these are the shapes that we get questions. Normally the disk, that point mass. Now you see point mass moment of inertia also mr square. But when it comes to what hollow cylinder also moment of inertia will be mr square. Now there are some similarities. Okay, now keep that in your mind. Now see that disk and hollow disk and solid cylinder, both of them have same moment of inertia, half mr square, half mr square. Just compare them. Just compare them and put a small short note. Prepare that. Okay. That so what's eight? Eight means hollow sphere. Moment of inertia of a hollow sphere, thin. Moment of inertia of a thin hollow sphere, sphere ni, of mass capital M and radius capital R about an axis passing to the center. About an axis passing to the center. About an axis passing to the center. Right? I think today we are learning some kind of important theory parts. These things you haven't learned also. So this story is important. We want to finish everything quickly. So just now, every time I'm asking feedbacks, ni, just compare with the other chemistry and biology or combined maths class. If you can give a small feedback. Now you all are, I think, going for online classes. I think. Then how the difference in this class and I think sometimes you are working more in my class. I think I don't know. You have to use your brain more in my class. I don't know. I'm not sure. If you can compare like that and if you can share a small message, it would be very helpful. If you have time, please do that also. Done, hands up, finished, hands up. We want to do next part. Finished, hands up quickly. This story finished, hands up. Only one. Quickly, quickly.
Now put you at the last, not last, the main topic. After doing this topic, we can do some questions in moment of inertia. MOI, MOI, moment of inertia, MOI. Write down important. Write down important. When there is a system of masses, when there is system of masses, comma, better you write on red color pen. When there is system of masses, comma, the total moment of inertia of the system, the total moment of inertia of the system, the total moment of inertia of the system, the total moment of inertia of the system about an axis equals to, about an axis equals to, about an axis equals to summation of moment of inertia, summation of moment of inertia, summation of moment of inertia, summation of moment of inertia of each mass, of each mass, of each mass about that axis, of each mass about that axis, of each mass about that axis. Right, okay. So now that story I will do when we'll do some questions. Okay, we'll do some questions. Right. Now this story. Now you know if there's a rotating sphere or if there is rotating cylinder or rotating rod, you know how to find the moment of inertia. Let's say now there are many masses and those masses are rotating around an axis. Then how do we find the total? If not, we can the resultant moment of inertia about the axis. How do we find that story? Look here. Now, now just think. Now in here, oh god, give me 1 second. Right now, this is your axis. Point two. Now there are many masses. This mass, let's say M1. You can't see. This mass is M1. The distance to the mass is, let's say, simple R. Just think these are point masses. Huh? Right? These are point masses. There are M1, M2, M3. Likewise, there are many masses. There are many masses. Okay. If not, let's say now this mass moment of inertia, let's say I1. Moment of inertia, this mass I1. There's another mass. This one's moment of inertia. Above this axis, let's say I2. And this mass moment of inertia is I3. The story is very simple. Now, moment of inertia is not a vector, right? Then there is no any big issue. If you want to find the total moment of inertia above this axis, O, you can write down the total moment of inertia equals I1 plus I2 plus I3. Not that much difficult. I1 plus I2 plus I3. So now is the story. Write the story and we'll quickly will do the page to take your tudes and page number. In your tude, take your page number in the tude. So we'll do question number uh, 26. Start doing 26. It's a good question. 26. Uh, 26, then 27, 25, 28. 26, 27, 25, 28. Start doing 26.
27, 25, 28. Start doing them. 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 Start doing. Hands up. Start doing 26 hands up. 26 start hands up. Now, if now the meter rule means a rod, very thin rod, then think properly. Meter rule is a rod, then think properly and do the question. It's not difficult. Uh, but they're asking, they are saying, in that case, they are saying, find the moment of inertia of a uniform meter roller of mass 0.56 kilogram. Uniform meter roller of mass 0.56 kilogram about an axis perpendicular to the roller passing through the 20 centimeter mark. Passing through the 20 centimeter mark. It's a good question. 26. 26 centimeter mark. 0.56. Meter roller. This max 0. 0 now meter. What is the length of a meter roller? Length of a meter roller will be how much? 0, 100 centimeters. 100 centimeters. This is 0 centimeter. Just this is 100 centimeter. Then your 20 centimeter mark will be somewhere here, not in the middle also. Uniform rod, but 20 centimeters not in the middle also. This is your axis of rotation. This will be your axis of rotation. Then you know that in this case, you know that this length will be how much? 20 centimeter. This gap is 20 centimeters. Am I correct? Then this gap will be 80. If it is 1 meter roller, 100 centimeter roller, this gap will be 80 centimeters. Now they are asking what is the moment of inertia of the roller above this axis. If in case if the axis is passing to the middle of the roller, that means if the axis passing to the 50 centimeter mark, then we can use that equation. What? I equals 1 over 12 ml squared. Mass is how much? 0. They have given the mass. Let's just given 100 centimeter. We can easily find the answer. But unfortunately, what happened here? Here, the axis is passing through 20 centimeter mark. In that case, what you should do? You should break this meter roller into two parts. Okay, this is part 1. This is part 1. This is part 2. If you break into two parts, then it's like that rotation of a rod passing through an axis through the end. So if the axis is passing through one of the end of the rod, what is the equation we learned? 1 over 3 ml squared. So you can easily find, see, now you broke the rule into two parts, part 1, part 2. So then it will be equivalent to this story. It will be equivalent to this story. This story, you know. So you know the story. If it is a rod, one of the ends, length is L, mass is capital M, means the equation is how much? 1 over 3 ml square. Right? Hands up, oh, understand up now, hands up. Up now, story is clear, hands up. Up now, story is clear, hands up. You understand, right? This story we know. If the axis is passing from the end and if you know the mass and length, then this story. You can add a story to here. So then what is the problem here? Then what is the problem here? The problem here is now you want to take separately, part 1, part 2 separately. Find the moment of inertia I1 in part 1, moment of inertia I2 in the part 2. If you want to find the total moment of inertia about this axis, this theory. When many objects are rotating about an axis, if you want to find the total moment of inertia, you want to add I1, I2 story. That's it. So then quickly find I1. What is I1? The total moment of inertia about this point is point O. So the total moment of inertia about point capital O, right? About point capital O, right? The moment of inertia, I can write down I total must be equal to what? Must be equal to moment of inertia of the part 1 rod is, I say I1, plus moment of inertia of the part 2 rod is what? I2. What is the equation to find the I1? 1 over 3. The problem is how to divide the mass. They have given the toe on. There's a problem. The problem you might get stuck that the mass, okay, overall mass of the rod is given as how much? Overall mass of the rod is given as how much? That is given as 0.56 kilograms. But how do I know specifically mass of 20 centimeter length and mass of 80 centimeter length? So common sense, all knowledge. 0.56 ni. Just think. This is your rod. I will now there are different ways. There are different ways to get this. Now this rod is uniform. I tell this rod is made with 5 chocolates. This is a chocolate bar, chocolate rod. Okay, this chocolate rod contains how many chocolates? 5 chocolates. One chocolate is length of one chocolate is 20 centimeter. The remaining 4 chocolates are here. Remaining 4 chocolates are here. Okay, there is one chocolate in the left side of the axis. There are 4 chocolates in the right side of the axis. Then, if I tell mass of one chocolate is 5 grams, reply everyone. Mass of one chocolate is 5 grams. What is the mass of remaining 4 chocolates? Reply everyone in the set box. Mass of one chocolate 5 grams. What is the mass of remaining 4 chocolates? 20. 20 grams. What is the total mass of chocolate bar? Chocolate bar total mass how much? 25 grams. The same story. So what you do, if you don't know the mass, you just take mass of this length segment is, mass of this length segment is, you take it as capital M. You don't know. Mass of this length segment, you mark it as simple lim. Simple lim. This part is simple lim. So length of this part is 20 centimeter. This part is 8 centimeter. Then you can think for simple M mass, you can write down. For simple M mass, you can write down length is 20 centimeter. For 20 centimeter length, you can for 20 centimeter length, the mass of the rod will be simple length. Then you can think for the 80 centimeter, if not for the 100 centimeter, it's up to you. For the 100 centimeter length, for 20 centimeter length, mass simple length. For the entire rod means 100 centimeter length, 100 centimeter length, what will be the mass? Hands up, how many of you understand for the 100 centimeter length, the mass will be 5 hands up? How many of you understand for the 100 centimeter length, the mass will be 5 simple hands up? Lord Malki. Can do, right? For one chocolate mass is 20, one chocolate mass is 5 grams, 5 chocolate mass is 25 grams. Do you understand? Then for the 20 centimeter length mass is how much? Mass is simple limb means for the 100 centimeter length mass how much? 5 simple limb. The total mass is 5 simple limb. This total mass 5 simple limb is given as how much? This 5 simple limb total mass is given as how much? 0.56 kilograms. The total mass of the rod is given as how much? 0.56 kilograms. Then what is the mass of one segment? Then the simple limb will be how much? Simple limb will be 0.1 1 2 kilograms ni. If you divide by 5, 0.1 1 ni, 1 1 2 kilograms. Then what is this mass? This one mass how much? So this part, now I understood, part 1 mass is 0.112. What is the mass of part 2? Part 2 is 4 times larger than part 1. This part 2 is 4 times than part 1. Then part 2 mass will be how much? 0.112 into 4. That means 0.448 kilograms. 0.448 kilograms. Genuinely hands up. The way I found the mass. If you really understood, hands up. Hands up. If you really understood understood, hands up. Okay, then they are easy. Now I was finding actually moment of inertia of part 1. So mass of part 1 is 0.112. 0.112 into the distance from the axis to the mass distribution. 20 centimeter square ni, r square ni. 1 over 3 mr square equation. R square means 20 centimeter. I want to convert to meters. Multiply by minus 2. Multiply by minus 2 whole square. Right? Whole square. Plus. So this is the moment of inertia of part 1. This is the I1. This is the I1 story. Plus I2 means again 1 over 3, the moment of inertia of part 2 from this axis. 1 over 3, mass how much? Mass is 0.448 into 80 centimeter square. R square means 80 centimeter. How do you convert centimeter to meters? Multiply by minus 2. Centimeters to meters multiply by minus 2. Whole square. The whole square. Now hereafter simplification is there. I think you can do it. Hands up genuinely. It's a very good question. Very nice question. This question is very clear answer. Story is very clear answer. It's a very good question. This is the practice you should get. Hands up. Did you understand? Some people they don't teach properly. 5:35 maximum. You are going to sit with me for half an hour. Start doing question number 27. Question number 27. Hollow cylinder of mass simple limb and radius simple are fitted with two lids. One of mass simple limb radius r. Find the moment of inertia of the system about the axis of cylinder. Very easy. Very easy. In terms of m and r, find the answer. Hollow cylinder. So that is not difficult. It's easier. Two lids means now we know lid means kind of disc. Lid means a circular thin disc. You know the equation to find the moment of inertia of a disc of radius capital R and mass capital M. Hollow cylinder means you know the equation to find the moment of inertia. Hands up who got the answer. Hands up. If you got the answer, hands up. Question number 27. Hollow cylinder. This kind of hollow cylinder. Okay. Now I draw the thickness. This has kind of big thickness, but normally it doesn't have a big thickness. Okay. For our understanding only, I'm drawing a hollow cylinder, and there are two discs. There are two lids. Radius capital R. This one hollow cylinder radius also capital R. This is your axis of rotation. This is the axis of rotation. Usual lid of radius capital R. Lid of radius capital R. Then what you want to do? So then, what is the equation you learn to find the moment of inertia of a? Now you can think this lid as what? The lid means we can consider it as a circular disk of radius capital R and mass simple lim. What is the equation we learn to find the moment of inertia of a lid of a disk? Half mr squared. Half mr squared. Half mr squared. Right, mass of the lid given as simple m, radius of the lid is given as simple r, hollow cylinder of mass simple m radius r, mass simple m radius r, mass simple m mass simple m. The equation to find the, now you can think this as a disk. If it is a disk, moment of inertia equation will be what? I equals half, we learned in terms of capital R, capital M, capital R squared. Hollow cylinder means the equation is this one. Hollow cylinder means I equals hollow cylinder. Hollow cylinder means I equals capital M, capital R squared, MR squared. This is also what? This is also a disk. If it is a disk, we know the equation. Disk means I equals half MR squared equation. So then you can find the total moment of inertia. You want to find the moment of inertia of the disk of this lid around this axis plus moment of inertia of the hollow cylinder around this axis plus moment of inertia of the disk around the cylinder. That is the answer. So you can write down I total means what? I total means you can write down. Not difficult. Learn these things again. So total moment of inertia about this axis will be total. How much? IT means I total. This is equal to what? This is equals to this one, this lid is what? Half mass simple m radius r squared simple plus hollow cylinder mr squared plus this one half mr squared. Finally, we are getting half mr squared. Half mr squared means mr squared. Mr squared means 2 mr squared. Hands up who got 2 mr squared before I get hands up? 2 mr squared before I take hands up. Not difficult, right? Then 26 done, 27 and 25. We'll do 25 and the 28. 25, 28. We'll do 25 and 28. Four small spheres of mass capital M each are attached to the vertices of a light rectangular wooden frame of length simply. Four small spheres. Find the moment of inertia of the system about an axis passing through one mass perpendicular to frame passing through. Find the moment of inertia of the system about an axis passing through one of the mass perpendicular to the frame. Perpendicular to the frame. Okay, that's a good question. That's a good question. Rectangular wooden frame. Four small spheres, mass capital M, vertices, right? Length simple. It's a good question. That's a good question. Question number 26. For your understanding, if I draw the diagram. For your understanding, if I draw the diagram. So the last 20 minutes that you are going to stay with me. Rectangular frame. If I draw a rectangular frame, the rectangular frame. Ni- Okay. Now there are four masses at the vertices of this rectangular frame. So this is the top view. When someone looking now, there's a frame. Just look here. This is a rectangular one, right? This is your frame. There are four masses, identical masses. All of them have same mass. Simple limb, point masses. Small spherical masses, point masses. Simple limb, sorry, capital limb. Capital limb mass is here. Another capital mass is here. Another capital limb mass is here. Another capital limb mass is here. So this frame is rotating about an axis passing through one of the masses. Just think this as the vertical axis passing to this mass, the vertical axis passing to this mass. Do you understand? This is that vertical axis. This is how your plate is rotating. Do you understand? This is how your plate is rotating. Then they are asking you to find the total moment of inertia. Okay. Up to now, question is very clear. Hands up. Up to now, question is very clear. Hands up. Question up to now very clear. Hands up. Question is very clear up to now. So then, if I do the masses, look here. Here, capital limb. This is capital limb mass. I take this is my axis. Huh? This is my axis of rotation also. Point capital O is this one. Capital limb. This mass capital limb. Capital limb. So then they have given this distance. Length is same length. Simple A, simple A, simple A, simple A. You can remember when the point masses are rotating,